Hi, everybody. This is Dr. Hicks, and this is the video to accompany the Chapter 10 lecture slides, which is all about nuclear physics. So this is all the stuff that we're going to talk about in this chapter, and these are the things that you should be able to do. The main thing is to be able to determine the missing particles in a nuclear reaction. That's where you actually have to solve some problems and do very minimal calculations, but there are still some calculations to do there. So this is what I want to talk about, a little bit about elements and isotopes. Then we'll really get into the meat of this, which is about nuclear reactions. And as always, at the end of the slides are the answers to the multiple choice questions or workout problems that are sprinkled out throughout the slides. Okay, so when we talk about elements and get into the next chapter 11, we're going to be referring to elements as how they're written on the periodic table, and some of their symbols make sense. Like aluminum, we abbreviate as Al, cobalt is Co. Some of them don't make sense. Gold is Au, and it does make sense because it comes from a Latin term. So when you come across elements where their element symbol doesn't match up to their name at all, it's probably because it was named something else originally, or its name comes from a different language. So most of the mass of the atom is all in the center, and that's at the nucleus. And that's contained in primarily the protons and the neutrons. So inside the nucleus, the protons and neutrons are very densely packed. This is kind of a cartoony picture of what that might look like. They're not hard spheres, but they would all be glommed together in one closely packed bundle. No electrons in the nucleus. And since protons are positively charged, the nucleus of the atom is always going to be positively charged. How big an atom is, like its physical size, is determined by how big those orbiting electrons are. And usually for most atoms, that diameter of the electron cloud is way bigger than the actual nuclear diameter. The electron cloud diameter is about 10,000 times bigger than the diameter of the nucleus. So there's a whole lot of mass in a very, very, very small volume. Okay, so when we talk about individual atoms, we're going to use the element symbol to name them, and then we're also going to list two numbers with that element symbol. Those two numbers that are important are the atomic number, which has the symbol Z, and it is the number of protons in the nucleus. For an electrically neutral atom, the number of electrons is the same as the number of protons, and that's just to balance out all the charge. The atomic number is what we use to identify the element. If two different nucleuses have different atomic numbers, they are different elements. If they have the same atomic number, it's the same element. Right? So that's why this is in bold. Number of protons determines the element. The mass number, A, is everything in the nucleus. So it's the sum of the protons and the neutrons. So mass number and atomic number are used to specify our elements. So just to reemphasize this point, the atomic number, that is what determines the element. So all gold atoms have 79 protons. You can change the number of electrons, you can change the number of neutrons, it's still gold. If you change the number of protons, then it's a different element. So the atomic number identifies the nucleus. So on the periodic table, X represents the element symbol. So for gold, it would be AU. Z is the atomic number. That's always going to be smaller than the atomic mass. And this is how we're going to specify our elements. So A, Z are always numbers. X is the element symbol. So it's going to be letters. Right. So if I have a particular sodium atom here, how many protons are in this? Okay, so let's talk about isotopes. I mentioned earlier that if I change the number of neutrons, I haven't changed the element. Nuclei that have the same number of protons but different number of neutrons are called isotopes. So iso kind of means the same. So they are essentially the same element but slightly different masses of the nuclei, because by adding neutrons, I add mass, but I don't change the charge. So shown here are all 3 isotopes of hydrogen. I know it's all hydrogen because there's 1 proton in the nucleus, and that's what defines hydrogen. So what's on the left is protium. So that's 1 proton, 1 electron. That is my main occurring version of hydrogen. Deuterium is an isotope of hydrogen that has an extra neutron. You can see down here, its symbol has 1 for the atomic number, but now the atomic mass is 2, because there's 2 things in the nucleus. Tritium is also an isotope of hydrogen because it just has 1 proton, but because it has 2 extra neutrons, its symbol is 1,3 hydrogen. So usually these isotopes don't have their own name, but for some they do, like hydrogen. So here is an isotope of carbon. This is carbon 12. I know it's carbon because the atomic number down here is 6. The mass number up here is 12. So that's the total of protons and neutrons in the nucleus. So I could figure out how many neutrons there are by subtracting the atomic number from the atomic mass. So 12 minus 6 is 6. So this has to have 6 neutrons. Carbon 14 is also an isotope of carbon. Same atomic number, 6, so I know it's carbon. Since the atomic mass is 14, this has 8 neutrons. So 2 extra neutrons than carbon 12. Still carbon though. Carbon 13 is also an isotope. And when you look up these elements on the periodic table, what you'll notice is that the atomic numbers are always whole numbers, but the atomic masses are decimals. And that's because on the periodic table, they take the average of the isotopes to get the average atomic mass. Okay, here's question number 2. The mass number of a nucleus is equal to the number of what in one of its nuclei? Okay, so when we looked at the cartoony picture of the nucleus, it was a whole lot of protons that are stuck together. Those are all like charges and they should repel each other, but they don't. And what's going on is that there is another force that's holding the nucleus together, and that's called the strong nuclear force. And what's weird about the strong nuclear force is that it only works for very short distances. So about the scale of the nucleus, the diameter of a nucleus. And it's attractive. So all of the stuff in the nucleus are called nucleons. So the protons and the neutrons, I can refer to those as nucleons. As those get closer and closer together, the strong force kicks in, and that is what's acting against the repulsive electrical force. So in really, really short scales, the strong nuclear force is stronger than the repulsive electrical force. However, when I get too many protons, and that magic number is 83, that's where the electrical repulsion of the protons finally beats the strong nuclear force, and the nucleus is not stable. And these nuclei undergo spontaneous decay, and that is called radioactivity. And there's a couple ways that these radioactive nuclei can come apart. They can either emit a particle, that's like a chunk of the nucleus comes off, small chunk, or they can just emit really, really high energy light. So that's what this second one is, high energy photons. So in those those break out into 3 decay processes. The 2 that emit a particle are alpha decay and beta decay, where in alpha decay, the particle that's emitted is the alpha particle, and in beta decay, the beta particle is emitted. Gamma decay emits gamma ray, which is the high energy photon. So it's not a particle, it's just essentially emitting a super, super, super high energy bit of light, way higher energy than even X-rays. So in this radioactive decay process, energy is always released, and that's because there's some potential energy in the nucleus that's from the strong force holding everything together. And these decay reactions take the form of A decaying into capital B, which is the daughter nucleus, and lowercase b, which is whatever particle was emitted. And in radioactive decay, the daughter nucleus is always significantly larger than this emitted particle, lowercase b. Okay, so the alpha decay process, that smaller particle is an alpha particle. It is essentially the nucleus of a helium atom. So this is an alpha particle. It's 4-2 helium, no electrons. So it's 2 electrons, sorry, it's 2 protons. The atomic number 2 means there's 2 protons and 2 neutrons, because 4 minus 2 is 2. There's 2 protons and 2 neutrons in the alpha particle, no electrons. Very, very important part to remember for any nuclear reaction, and that includes nuclear decay, is that the total atomic mass on either side of the reaction arrow, this arrow is the reaction arrow, the total atomic mass has to be the same before and after the reaction, and the total atomic number also has to remain the same before and after. And knowing that is going to allow me to predict or figure out what these missing decay particles have to be. So remember this. So let's figure out what happens when the nucleus of a uranium-238 decays by emitting an alpha particle. So first thing we have to do is write down the isotope of uranium-238. The 238 is the atomic mass. So that's the bigger one. It's not the atomic number. I can figure out the atomic number by going to the periodic table and looking up uranium. Its atomic number is 92. So the symbol for uranium-238 is this, U-238-92. So that's what I'm starting with. Now it tells me that it decays by emitting an alpha particle. So I replace these question marks on the right side with the daughter nucleus that I need to find, and the alpha particle here. So this is the lowercase b, missing particle is the uppercase B, and what I'm starting off with is the capital A. So this is A splits off into capital B plus a lowercase b. Capital B here, that's what I got to find. So now I've got to apply the two rules about having the same atomic number on either side of the reaction arrow and the same atomic mass on either side. So on the left side of the arrow, my total atomic mass is 238. So that means over here on the right side, I also have to have 238. The helium, or so the alpha particle contributes 4. So what do I have to add to 4 to get 238? 234. So I figured out the missing atomic mass of the daughter particle. Now I apply the second rule to figure out the atomic number of the daughter particle. And once I know the atomic number, I can look at the periodic table and figure out the element symbol. So this is the same thing that I did before. I start off with an atomic number of 92. The alpha particle contributes 2. What do I have to add to 2 to get 92? 90. So the atomic number of the missing particle is 90. So quick trip to the periodic table tells me that the element with the atomic number of 90 is thorium, and its symbol is it's TH. So now I know my missing daughter nuclei is 234 thorium. So by specifying the 234 with the thorium, I've completely told you what the isotope is. 234 thorium doesn't get its own name, so that's why we have to use that naming technique. So the atomic mass along with the element. So 234 thorium, that's the missing particle. So all of that, here it is down here at the bottom. Here's thorium 90. So I looked that up to complete that. Now in beta decay, the beta particle is an electron, right? So how can the nucleus emit an electron if there's no electrons in the nucleus? Well, what happens is a neutron can spontaneously convert into a proton and an electron, and that electron gets emitted from the nucleus. Now, in order to take care of the atomic number changing as because we're adding a proton, the symbol for a beta particle is this. And I know that's kind of weird. Its atomic number is -1, and that's to account for the fact that to create a beta particle, we had a neutron convert into a proton and an electron. So by adding a proton, we have altered the atomic number to make sure that to keep everything balanced out, we have to put a -1 here to counteract the addition of this extra proton. Since this beta particle is just an electron, it has no neutrons, so its atomic mass is 0. Right? It's a weird particle, but it does not break any of the rules for how we name things. We just have to have these weird numbers to make sure everything balances out. So let's work through the nuclear decay when carbon-14 emits a beta particle. And this is going to work a lot like what we did before. First, we got to write down the isotope of carbon-14. So from the periodic table, I know that its atomic number is 6. So this is my starting point. It emits a beta particle that's given to us. So on the right-hand side, I'm going to have my missing particle that I want to find and the beta particle. So at step number 2 here, right here, I've got to where I can start applying the rule about the atomic mass being the same on both sides and the atomic number being the same on both sides. So total atomic mass on the left is 14. Beta particle contributes 0. So my missing particle has to have an atomic mass of 14. I start off with an atomic number of 6 on the left. The beta particle contributes -1. But do I have to add the -1 to get 6? 7. So this is kind of the weird step with the beta decay, that I have this -1 for the atomic number. But you work it the same way you do everything else. What do I add to the -1 to get 6? That's just doing this little bit of addition right here. So then my missing particle is this isotope of nitrogen, 14 nitrogen. So total atomic mass is the same on both sides, and total atomic number is the same on both sides. That's how you do all of these radiation type problems. All right, so just to kind of wrap up some of the radioactivity for now, and then we'll get into some of the other types of changes that nuclei can undergo. The atomic mass is always going to be the bigger of the two numbers between atomic mass and atomic number. So one way that you can tell the two apart is that the bigger one is the atomic mass, and it's on the periodic table, that's the one that's going to be a decimal because it's an average of all the isotopes. When you go to use that decimal atomic mass on these types of decay problems, you round it to the nearest whole number. And then beta decay is a little bit weird, and that's just because it has a negative number for the atomic number. It's -1, because it's a negatively charged particle, and to balance out the creation of a negatively charged particle, we had to add a proton. And if we add a proton, that would mess up the atomic number. So to undo that, we subtract 1 from the atomic number. This is kind of weird with the beta decay. Luckily, for gamma decay, since there is no actual particle emitted, there's no change in atomic mass or atomic number, so just a loss of energy. So when an element undergoes gamma decay, does not change into a different element. It just loses energy. Now, there's another way that I can get energy from nuclear reactions, and that's from either combining two smaller nuclei to form a bigger nucleus that actually releases some energy, even though I'm putting two small things together to form a bigger one. The bigger one has a lower potential energy, so that energy comes out, it's emitted. And in nuclear fission, if I split a nucleus into two smaller nuclei, that also emits energy and emits neutrons. So both by putting nuclei together to make a big one or by splitting a big one into a smaller one, energies emitted in both cases. So I know uranium is unstable, and I know it's unstable because it's one thing. Its atomic number, 92, that is higher than 83. So 83 is the magic number where you have too many protons and it's unstable after that. So just the fact that uranium has an atomic number over 83, I know it's going to be radioactive. And one possible way that it can take care of it being unstable, in addition to like alpha decay, it can just randomly split into two smaller nuclei. And this is one possible splitting where one nucleus that's left over is krypton, and the other nucleus that's left over is barium. And then some other unknown particles are also emitted. But just like radioactive decay, I do the same rule of total atomic mass and the total atomic number on either side of this arrow has to be the same. That's the trick to doing all of these nuclear change problems. Atomic mass is the same on both sides. Atomic number is the same on both sides. So let's do the atomic mass first. So it's 236 to start with. 88 and 144 add up to 232. So what's missing is an atomic mass of 4. So just as it stands with the krypton and the barium, there's not enough atomic mass left over. So I need an atomic mass of 4 for this missing particle. Now I've got to figure out the atomic number of that missing particle. And it's the same thing. Balance out the atomic number on either side. I start off with 92 on the left. That's from the uranium. 36 and 56, that adds up exactly to 92. So I'm not missing any protons. So the missing particle has to have an atomic number of 0. That sounds kind of weird. What is a particle with an atomic number of 0, but an atomic mass of 4? Well, how many neutrons is that? Subtract the atomic number from the atomic mass, and you get the number of neutrons. 4 minus 0 is 0. This is just 4 neutrons. So what's missing, what the missing particle is 4 neutrons. And I figured that out because the atomic number was balanced. So I wasn't missing any protons, and that means I'm not missing any like nuclei. So that has to be a neutron. And this is a symbol for how we write a neutron. It's 0, 1, and then the lowercase n. 0 because there's no protons, just like a beta particle. Beta particle had 0 neutrons. Neutron has 0 protons, but its atomic mass is 1. So this is kind of similar to how we wrote the beta particle, 0, 1, n. So this is the complete nuclear reaction. And the way that we write these 4 neutrons, instead of having a 4 as the atomic mass, we put a coefficient of 4 in front of it. Because those 4 neutrons aren't together as a nucleus. They're just going to go in 4 random directions. There are a whole lot of other possible nuclear splittings that uranium could go through. Which when that happens, which particular one happens, you can't predict. It's completely random. However, we can get probabilities for different splittings happening, so we can know probabilistically what uranium would most likely decay to. So here's a couple other examples of how uranium-236 can undergo nuclear fission. Top one, it splits off into xenon and strontium and some 2 neutrons. It could also split off into tin and molybdenum and 3 neutrons. In all cases of fission, neutrons will be emitted. So I want to talk a little bit more about these uranium for a little bit, because it's used in commercial nuclear reactors as a fuel, and that's important. It's important technology to understand how that works. So the uranium-235 is a more stable isotope than the uranium-236. So just having one less neutron makes it a little bit more stable. So if I were to shoot a neutron at a nucleus of uranium-235, that would immediately change it to uranium-236, and that makes it very unstable, and that would immediately split into 2 other smaller nuclei, and then emit more neutrons. So what's important here is I'm putting in 1 neutron, and I'm getting out 2 neutrons. So I'm getting out more neutrons than I put in, and they're just being released from this big nucleus. But that's an important part of the fission process, because those 2 neutrons that I created, if those each hit another uranium-235 nucleus, that could make that split, and that could keep on going in a chain. That's a nuclear chain reaction. If you can control that safely, then you can possibly create a nuclear reactor and generate electricity. The smallest amount of nuclear material that can sustain a chain reaction is called a critical mass. So as soon as I get up to the critical mass of the material, I can get a chain reaction going. So here's a picture of that expanding 235 reaction. And if I had a whole lot of uranium-235, this could go on for a long time. This could just keep doubling at every step. And that could possibly be bad. So what I want for a self-sustaining chain reaction to proceed, I have to have just the right amount of fissionable material, which is the uranium-235. If I have too little, this chain reaction stops. If I have too much, I can get an expanding chain reaction. So critical mass is the minimum amount of the stuff I need to sustain a chain reaction. For uranium-235, it's about 4 kilograms. I say about because the actual critical mass is probably pretty hard to find. Below the critical mass, you don't get a chain reaction. Above the critical mass, you get an expanding chain reaction. That expanding chain reaction, that can be the bad one. So here's just a picture of subcritical mass, so too little stuff. All these neutrons that are produced just end up escaping. They don't hit another uranium-236. Over here on the right, that's a supercritical mass where most of the neutrons that are generated stay inside and just create more fission reactions. So very few neutrons escape relative to how many are stuck inside. So uranium is a common fuel for nuclear reactors. The isotope of uranium that's most commonly occurring on Earth is uranium-238. All right, sorry, one of my colleagues knocked at my door and I had to go answer. Natural uranium is almost all uranium-238, and we really need uranium-235 for nuclear reactors. That's the fissionable uranium that works as fuel. Only 0.7% of naturally occurring uranium is the kind that can use for fuel. So you have to enrich naturally occurring uranium to get to where you have enough of the 235 isotope. For nuclear reactors, you need to enrich it to about 3% uranium-235. Nuclear weapons require their uranium to be enriched to a much higher percentage, so roughly 90% uranium-235. And that's why if you hear on the news about some country having enriched uranium and enriching beyond a certain percentage, the worry is that, are they using it for nuclear fuel, low percentages, or nuclear weapons, higher percentages? So atomic weapons use a supercritical amount of fissionable material to have a sudden release of a huge amount of energy. The way that these usually work, since you can't have that supercritical mass together, otherwise it'll explode, you have like that divided into little parts, and a conventional explosive is used to force all those subcritical chunks together. It becomes supercritical and then essentially explodes because all that energy is released. On the other hand, so nuclear reactor uses a controlled fission process to generate energy. And the way that they control it is they have some material like boron or cadmium that can absorb neutrons. So having too many neutrons is what's causing the reaction to go out of control. So these cooling rods go into the fission reactor and they absorb neutrons, and that slows down the reaction. Water is also used to control the reaction by absorbing just some of the thermal energy. And that's how you get electricity from a power plant, nuclear power plant. That cooling water is used to generate steam, and that generates electricity. If you lose ability to control the reaction rate, that's when you have a nuclear meltdown. And a nuclear meltdown is literally that. It's when the fission reaction gets so hot, it just essentially melts through the floor. So we had one in the United States in '79 at 3 Mile Island. That one was relatively minor. There was very little contamination. That's where Wolverine fought Deadpool in that Marvel movie. The meltdown at Chernobyl in Ukraine was terrible. That was due to a very poor reactor design and bad safety issues. that had an explosive release of dangerous radioactive material that uh, spread all over the Earth. Now, more recently, the Fukushima Daiichi reactor in Japan, when the tsunami hit, that one was really bad because they lost power. The nuclear power plant lost electrical power and they could not stop the reaction, which seems ridiculous, but that's what happened. A lot of radioactive material ended up going into the ocean because they had to just spray ocean water on that reactor to keep it cool so it didn't explode. And because of this, there's a lot more regulations on nuclear reactors design now. Okay, so question 3, what's the missing element in this nuclear reaction? This is a nuclear fusion reaction, and I know it's fusion because I have 2 small nuclei coming together to make this nuclei plus some missing stuff. And when you go and work this out yourself, you apply the same rules as before. Atomic number is the same on both sides, and atomic mass is the same on both sides. And that's an example of a fusion reaction, where you have smaller nuclei coming together to form a larger nuclei and release energy. This fusion reaction is what powers stars. Stars are almost all hydrogen, and in that reaction, there's so much gravitational force holding those hydrogen atoms together that they can be compressed to where they fuse together, and 4 hydrogen atoms can fuse together to form a helium atom, plus some electrons that are left over, and a lot of energy. So notice, just real quick, this is an electron. That is not a beta particle. This is not beta decay. This is a real electron being emitted because there are it's a real electron beam. It's not the creation of a beta particle from the decay of a neutron. And I know that because what's up here, if the atomic mass is 1 and the atomic number is 1, 1 minus 1 is 0. There's no neutrons to start with. Here's a couple other examples of some fusion reactions. Here I have 2 deuterons. So those are hydrogen isotopes fusing into tritium and a single proton, or deuterium or a deuteron and a tritium isotope fused together to form helium, which is an alpha particle, and an extra neutron. So this is just a cartoony picture of what happens. But these are all reactions that occur inside of stars. The reason we don't have any fusion reactors generating electricity right now is that it's really, really hard to push together the positively charged nuclei to get them to undergo nuclear fusion. It's possible in stellar conditions, like for a star, because the gravity is so strong. Because there's so many particles under their own gravity. To do that on Earth, we have to find some way to get these to fuse, and it usually involves heating them up to really, really, really high temperatures, and then using like magnetic forces to get them to fuse together. We are really close to that right now, technology, but it's very hard to get the temperature and confinement of that high temperature material accomplished. But that's the goal, is to have a sustained fusion reaction, because that would be a big first step towards clean nuclear energy. Right now, nuclear fission reactors generate a lot of radioactive daughter nuclei, and those are radioactive for a long time, thousands and thousands and thousands of years. So last thing I want to talk about here are some of the biological effects of radiation and when that can be bad. When radiation has enough energy to remove electrons from atoms and cause them to form ions, that's when we have bad radiation. Alpha particles, beta particles, gamma particles, neutrons, gamma rays, X-rays, those are all high energy radiation that can cause ionizing, which is the kind of radiation that could kill you. Somatic effects of radiation affect the recipient. So that's if you're getting dosed with a lot of radiation, it affects you. If you get some dose of radiation and that causes your offspring to have genetic changes, that's a genetic effect, which is definitely something that can happen. People that work in conditions where there's radiation exposure potential have special badges that they wear that get checked routinely to make sure they did not get too much radiation, because you can't see, smell, feel, taste any kind of ionizing radiation. Okay, so that's the end of chapter 10. There's a couple questions whose answers are about to follow. So hopefully you've worked those out before you check the answers.